Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto. Mungu ibariki Tanzania na watu wake. Ibariki Tanzania, ibariki Tanzania, tubariki watoto wa Tanzania.
The circular coil, at this moment we can consider it with a single turn. And in this circular coil, it means we have a constant radius, we call it R, listen carefully. But this circular coil is carrying current, which we call it I. Stop writing. Current is calling I. And then, because it's carrying current, it generates magnetic field. So the business that we have to do right now, because we have, it means that also, if you want to know the length of this circular coil, it will be the circumference. So you can have L, just like this. Listen careful. Listen careful. Okay. So this is the length L, so this is the circumference. Then we want to find the magnetic flux density at point B. P. So at point B, we want to know the magnetic flux density at the center. So this is what it, this is equal to center of the circle. So remember that the principle we said from the curved circular, the curved carry conductor, we have to take a small segment. So similarly, even here in this circular coil, we have to take a small segment. And this small segment now, it will have a length that we call it dr. Alright? dr. And then the angle here which will be made between this conductor and the line will be 90 degrees. So the angle is 90 degrees. So let me write, because of the way that I do it, is 90 degrees. That's the angle between the line and the conductor. Okay? So it means that is what it is, 90. Let me just write this way. So this is 90 degrees. Okay? That is the next concept. So now, we know the distance from here to here, it's what? It's R. So the distance from here, from the center to this small segment, it's R. Are we together? So we have a current that is flowing, maybe from in this direction, so the current is circulating. Then from there, we want to know what will be the magnetic flux density or small segment of this magnetic flux density at point P, which is the center of the cycle, due to the small L segment of the cycle. Are we together? So that is this is all about your figure 221, which means what? It means that the magnetic flux density at center of circular coil. Okay? Yes. So then we come into second stage. Second stage, we say that we call the Biot-Sarvat law of 40. So the Biot-Sarvat law formula of small segment, I'm increasing information, small segment of 40 of conductor. So the magnetic flux density at the point due to the small segment is delta T, delta B. So this is delta B. Stop writing. This is equal to what? Permittivity, yeah? Is it permittivity or permittivity, yeah? Permittivity of the free space, times electric current, times small change in length, times sine of angle theta divided by 4 pi r square. That is Biot-Sarvat law of the small segment. But we want to derive the formula, the Biot-Sarvat formula, that will give us the maximum magnetic flux density at the center due to the whole circular coil, not a small segment. Are we together?
Yes.
Our intention, we want to know the magnetic flux density at this center of the circular coil due to the every part of this circular coil, not only due to this small segment. So this is the formula, this is the Biot-Sarvat formula that gives us the magnitude of magnetic flux density at the point from any point at the conductor due to the small segment dr. Are we together? So then we go to the steady state. The steady state, we say that from figure 2.1 above, the angle, which is theta, the angle between line joining what? Joining the point center of the circular coil and what? Okay, joining center of the circular coil to what? The point P, okay, and to the circular coil, is right angle. As I have shown there, right angle. Mean that it's 90 degrees. That to say, sine of 90 degrees is the special angle. Is it got right?
1.
1. For that case now, the formula there, which is small change in magnetic flux density, is equal to permittivity of the free space times electric current times dr over T over 4 pi r square. So this is our equation 1 and this is our equation 2. If you want to master the derivations of the formulas in physics, do one thing at a time. Do one thing at a time. You will be deriving formulas carefully and with great precision. So here it is, we are in first state. The first state, we say that to find the magnetic flux density at center of circular coil due to center of the circular coil due to it. To find the magnetic flux density at the center of the circular coil due to it, due to the wall circular coil or due to the entire circular coil, due to the entire circular coil, then you have to integrate have to integrate equation to both sides. Why should I integrate? To find the summation. Find the summations of the magnetic flux lines of the different small segments combined together to form the entirety circular. So, ladies and gentlemen, here we have equation 2, which is small change in magnetic flux density is equal to permeability of free space times electric currents times dr of what? Over 4 pi r squared. So we integrate, we apply integration to both sides. So writing, here we have to integrate from 0 to the magnetic flux density. This is the lower limit, this is the upper limit. Here we have to integrate from 0 to the length, to the total length of the circular coil. Are we together?
Yes.
Be careful with this part of integration. This is the way that you see applications of basic applied mathematics for the PCB students. So if that's the case, we say that we integrate from 0 to magnetic flux density. So listen, here I used to tell you that, listen, the technique we are using. Here you have magnetic flux density power 0. Anything power 0 is 1. And then say 40 times small change in magnetic flux density. Okay? On this, on your right hand side, permeability of the free space, electric current, 4 and pi, and r, or the distance r, are constants. So you have to take them out of integration. Joshua is Joshua. Then times 40 electric current, over 40 over 4 pi r square. Then so integrate from 0 to the total length of the wall length of the circular coil. If you don't listen, you just see B power 0, which is not in the previous step. As I should claim, or as I should say that Olenjolai is complicating derivation. Why it's not a 2? Why did I introduce it? Because we want to integrate delta magnetic flux, I mean small change in magnetic flux, but we cannot integrate a small change of magnetic flux without having the magnetic flux itself. So whenever you find you are integrating magnetic flux, small change in magnetic flux, it means that magnetic flux is there, but it's power 0. So to integrate this physical quantity, on this side also, we have what? So on left hand side, you have integral from 0 to magnetic flux. You have magnetic flux density power 0, dB. This is equal to what? The limit of free space, times electric current, over 4 pi, square of the distance from the point to the conductor. Also on this side, we have to integrate from 0 to L. Here we have L power 0, then the L. Okay. Are we together? So this we can make intermediate equation 3. Okay, so to integrate that, we got the fifth step. We integrate by what? Integrate by substitution. So integrate both parts, both sides of equation what? Equation 3 by substitution. Not actually by substitution, means that by using formula. By using formula. And which formula? This one. That we used to teach in basic applied mathematics, that if you integrate from A to B, then you have x power n dx. This is equal to what? This is equal to what? Ladies and gentlemen, x power n plus 1 over n plus 1, and then from the lower limit, upper limit. So for this formula, to integrate on the left hand side. So on the left hand side, we have integral from 0 to magnetic flux density. The magnetic flux density power 0, there's small change in magnetic flux. Right? So if you check this formula, Ne8 is 0. dB is equivalent to dx. So the next step now, we have what? What are we going to find? The answer is this one. X power n. So what is X? Magnetic flux density. What is n? Power 0. Plus what? Plus 1. Over what? N. What is n? 0. Plus what? Plus 1. And what is the lower limit? 0. Upper limit, magnetic flux density. So then, if that's the case, so you say if you integrate from 0 to magnetic flux density, magnetic flux density power 0, then students used to claim how to integrate this one. And I used also to have those weak students who don't love BAM and don't love advanced mathematics. 0 plus 1 is 1, 0 plus 1 is 1, so B power 1 over 1, the answer is B. From what? 0 to B. So now, substitute the limits. Here we have upper limits, so if you put there, we have upper limit minus what? Minus 0. So on the left-hand side, we have B. So on the left-hand side, if you integrate from 0 to magnetic flux density, power 0, dB, this is equal to B, and this will make equation what? 4. Wonderful. Now physics is coming. You are friend. Okay. So if we consider now the same formula, so the sixth stage, if you consider what? Consider the right hand side of equation what? Of equation 3. What do you have on right hand side? You have permeability of free space times electric current over 4 pi times square of the distance. Then we have to integrate from 0 to L. Then here we have L power 0 dr. Stop writing. So if you use this formula, these are the constants. We keep them out of the integral. So permeability of the free space times electric current over 4 pi r square. Then we have square bracket. So here we are. So here we are the x, and here our x is L. Then here we have n is equal to 0, so you have 0. So you have 0 plus 1 on the right hand side. Divided by what? N, which is 0 plus what? Plus 1. Then this one, we say from 0 to what? To R. So it means that permeability of the free space times electric current over 4 pi. I'm using a very simple, and this is simplified derivations I have ever seen in my life. So this is L power 0, but for the lazy student, don't care. So here you have 0 plus 1 to be L power 1 over 0 plus 1, L power 1 over 1. So the final response there will be L from 0 to R. Substitute the upper limit. So instead of L, we have L. The lower limit is 0. Substitute there, you have 0. So L minus 0 is L. But remember that here I forgot to introduce a constant. So for this case, it is mu I over 4 pi r squared. And then we have what? L. From 0 to L. So this will make your permeability of free space times current over 4 pi r squared. Then we substitute L, so L, substitute L limit which is 0. So on the left hand side, we have an assignment to integrate from mu naught to L. Okay? Mu naught to L over 4 pi r squared. Okay? Then so we have to integrate it. We have to integrate 0 L power 0 dr. And our finding is what? Mu naught I L over what? 4 pi r squared. So this will make equation what? 5. So now we have to substitute equation 4 and 5 in equation what? Then I'll tell you the next story. Have you finished to copy? Let us substitute equation 4 and equation 5 in equation 3. Substitute equation 4 and equation 5 in equation 3 above. So what is question 3? On right hand side of question 3, for question 4, have magnetic flux density. Then on right hand side of question 5, if you want to substitute in question 3, we have what? Permeability of free space times electric current times length divided by what? Divided by 4 pi r squared. So this will form what? Equation 6. So new equation 6. Then we go the 8th step. The 8th step we say that the length of the circular coil is equality circumference. The length of circular coil is called the circumference. It's called the circumference. The length of circular coil is called the circumference. We say the length of the circular coil, for example, suppose that this is the circular coil. So the length of this circular coil is the circumference. It's this one, this entire length. This is what we call the circumference. Okay? And then from what we taught you since primary education in Tanzania, I learned myself this concept for the first time in 1990, when I was in primary education, and I learned in Swahili language, we call it mzingo wa duara. Mzingo wa duara means the circumference of the cycle. So, mathematically now, circumference of the cycle. So the length, which is equal to the circumference of the cycle, this is given as 2 pi r, or this is given as pi d, where d stands for diameter and r stands for the radius of the cycle. So simply, for that case, the length of the circular coil is equal to twice pi r. So this will make it equation 7. So now, to derive, means that to finalize the derivations of the formula of the magnetic flux density at the point from this magnetic flux density at the center of the coil, of the circular coil, then we got the 9th step. For the 9th step, we say that substitute question 7 into question 6. So question 7, on the left hand side we have magnetic flux density. On right hand side we have a bit of free space. Then times current over 4 pi r square times length. But this length is what we found in question 7. So the bit of free space times current. Then we have 4 pi r square. Then we have what? We have the circumference of the cycle is 2 pi r. So magnetic flux density, the magnetic flux density is equal to twice the permeability of free space times current times pi times radius over 4 pi distance square. Because the radius is just distance also for the circular coil. Because we say that this is the radius of the cycle, which is the distance from the point to the circular coil. So you can simplify here by pi and pi, you can simplify by 2, there we get 2. And then you can simplify, you can divide by r, to both numerator and denominator. Here will remain is 1, here will remain is R. So magnetic flux density at the center of the circular coil is given as products of permeability of the free space and current or voltage over twice R. Are we together? So this is the formula we deduce. But again, we say that this formula is for the circular coil. For the circular coil that has what? Has single turn. A single turn. This number of turns is equal to 1. This is the formula. So we say that in electromagnetism, the circular coil may be constructed by many turns, by using it, by windings of many turns. So we say that now the Biot-Sarvat formula at the center of the circular coil for many turns, for n turns, is given from this. So we say that for many turns, which is n, many turns of the circular coil, the magnetic flux density is equal to permeability, free space, times current, over trace R. So in that to find for the several turns, you have just to multiply this number of turns. So the magnitude of magnetic flux density is equal to permeability of free space times number of turns times sorting times current or volt raised up. So this is the Biot-Sarvat formula for n turns for that determines the magnitude of magnetic flux density at the center of the circular coil with several number 40 of turns. It's not difficult for serious students. Okay, so from there, now we can solve the problem. This problem is called example 2. Please, online students, don't spend your time on doing two things, sleeping or slumbering and learning physics. This is the example 2. Example 2, we have Roman A, derive an expression, or some of the exams they just ask you write down. So derive an expression for for magnetic flux density. Magnetic flux density at the center of the circular coil, center of the circular coil, or Flavius ara. Flavius ara having entrance and the carrying current I. And this is homework. This is homework 2. So practice. Stop the video and then practice. Try to derive result referring any information that I've presented to you. B. Okay, so in order to avoid confusion with students, this is that example 2. So example 3 is this. A circular coil of diameter 2.0 -3 meter is made up by 100 tons of wire. $100 tons of wire. And carries a current, of 40 or 5 milliampere. Calculate. Calculate the magnetic flux density at the center of coil. Given bit of free space is equal to 4 pi exponent -7 Henry per meter. So to answer example 2 is just refer to notes I've told you. Everything is at your fingertips about example 2. So that's why I say that this is homework. So maybe experience to see that the homework is written here. So homework 2. For example 3, okay, we can do computations together. Because we'll be asking questions in advanced certificate secondary education examination for the TANZANIA. So let us read the question. A circular coil of diameter 2 exponent 3 meter is made up by 100 tons of wire and carries a current of 5 milliampere. Calculate the magnetic flux density at the center of the coil. Given the availability of the free space is 4 pi exponent -7 Henry per meter. So you can also, because I'm using the method we call it in teaching or in training, active learning method. Say active learning method. The active learning method, we are trying our level best to make students to be a center of learning. How? If we write a questions or we put the questions on the blackboard before we solve, it's better for you as the students to try to solve that questions even on graph paper and to see your findings. And then after certain times, then we do the corrections or solve it for you. That means of active learning students, or we call it student-centered learning system. Are you ready for that? But for advanced students of TANZANIA, they'll tell you, teacher, just solve questions for us. We'll solve in next exam. So solution for example 3. Let me read it if you don't see it. Maybe you cannot read the questions clear. A circular coil of diameter 2.0 exponent -3 meter is made up by 100 tons of wire and carries current of 5 milliampere. Calculate the magnetic flux density at the center of the coil. Given the availability of the free space is 4 pi exponent -7 Henry per meter. So the first step, we say that data given. Okay, so the data given, we say that what are you be given first of all? Diameter. So you can pause the video and then try to solve this problem yourself. So diameter is 2.0 -3 meter. Then we have again another piece of information, number of tons. Number of tons, which is M. Number of tons is equal to what? 100. Of wire and carries a current of 5 milliampere. So current, which is I, 5 milliampere. It's 5, so -3 ampere. Calculate the magnetic flux density at the center of the coil. You have to find magnetic flux density, which is B. And this is what is required. Then you have what? Permeability. Or free space. It's better. I know some students, they say, sir, we are redeeming time. Let me use these symbols. No, it's better to define what are they. So permeability. Is it permeability or permittivity?
Permittivity.
Huh?
Permittivity.
Permittivity, not permeability. Huh?
Yes.
I used to confuse these two terminology, permittivity and permeability.
Yes, permittivity.
It's permeability. It's called permeability. Did I say permittivity in session 1? Okay, do correction. So it is what? Permeability. It is permeability. Do correction for what you have written in session 1. It is permeability. So this is given as what? 4 pi. So -7 Henry per meter. Do corrections in your note sheet for the session 1. I made a mistake. Instead of calling permeability of free space or permeability of the medium, I called permittivity of the medium. Okay, so that's the first step. Then we go for the second step. So the second step, you have 2 options because this is the question of the the questions of paper 2. Remember that the questions of electromagnetism in advanced certificate secondary education examination in United Republic of Tanzania, it's questions for advanced physics paper 2, which worth so many marks, which worth actual that more than 20 marks. Listen carefully. Listen, you can be maybe using a calculator and calculating now, but you can lose this question because of your ignorance of the information, so because of your taking easy stuff. Listen carefully. Most of the questions of topics of paper 2 which need formulas, you should derive the formula before you do computation. That's the trick. Why? Because advanced physics paper 2 or advanced chemistry paper 1, paper 2, or maybe advanced mathematics paper 2 is defined as long explanation exam. It's not a short like in paper 1. Paper 1, you can recall a formula, then you just substitute what the physical quantities that will be given, off you go. But for paper 2, you have to derive first the formula. And there are some marks you will win from the derivation. That's the trick I give you. So the second step, you say that derive the formula, the Biot-Sarvat formula that determines magnetic flux density at the center of the circular coil. So to derive this, I tell that refer notes. You can ignore what I'm telling you, but one day you will tell me that what you have said it is true. So refer notes for the derivation, and finally for the magnetic flux density is equal. So for you local students, if you reach here, don't write refer notes, derive it. That's the moment for you to do practice. Take easy this stuff, will tell me. So permeability of this is permeability of the free space times number of turns times electric current divided by what? By twice of the distance from the center to the circular coil. So we are looking for the magnetic flux density. So after deriving the formula, now we can go to the third step. Third step, we say that compute magnetic flux density at center of the coil. So magnetic flux density at the center of the coil, the permeability of the free space is 4 pi, so -7, multiplied by the number of turns, which is 100, then multiplied by electric current, which it is 5, so -3 over twice. Radius, remember that radius is equal to diameter over 2. So radius of the cycle is the diameter over 2. So what the diameter is 2.0 to negative 3 over 2. So we can simplify this to these two. We have final magnetic flux density is equal to 4 pi exponent negative 7. 100 times this one will remain is 5 exponent negative 1 over 2 exponent negative 3. So you use your scientific calculator, and the unit of magnetic flux density is Tesla. So if you use your scientific calculator, you find the magnetic flux density at the center of the circular coil is 3.14, so negative 4. It's 1.4, so negative 3 Tesla. 3.14 exponent negative 3 Tesla. 3.14 exponent negative 3 Tesla. Magnetic flux density. Magnetic flux density at the center of the coil is 3.14 from negative 3 Tesla. Okay, so that's the final solution for example 3. If you have any question, don't hesitate to ask in the comment section, and I'll try my level best to answer your questions. Okay, so that's all about it. You can do more questions about finding magnetic flux density at the center of the circular coil. So now, let me teach you the second formula, the second derivation. And this is all about your derivation. This is 2.2. Derivation of Biot-Sarvat formula that determine magnetic flux density on the axis of circular coil. So the derivation of Biot-Sarvat formula that determine magnetic flux density on the axis of the circular coil. Okay, so we are here to teach you about the derivation of Biot-Sarvat formula that determine magnetic flux density on the axis of the circular coil. So, I say, if you want to do two things at a time, especially in advanced physics, you lose one. So the first step, we say that consider the axis of circular coil. Circular coil as shown in figure 2.2 below. So you have a circular coil here. So this is the circular coil. Then this circular coil, here we have an axis. Okay, so this is the center. Say center, say O. This is the circular coil. So you can start this one turn and then later we change it. It means that you think for the more turns. So this is our point P today. So we say that the axis, when you say about the axis of the circular coil, means it's a line passing through the center of the circular coil. It's a line passing through the center of the circular coil. Again, and do against the top. Okay. So this is point P. Here we have again another point. So this is point P. Where we have to find magnetic flux density. So we find magnetic flux density, this is the axis that is still passing through the center to other side. So if you have, for example, a disk, and then you have a disk, suppose that this is the disk, when you say about you determine the magnetic flux density on the axis of the circular coil, we mean that is the axis of rotations. For example, if this is the disk, then the axis of rotations is passing by here. So suppose that this is your circular coil, and this is the axis of rotation. This is the axis passing through the center. So you want to find the magnetic flux density at this point, but on the axis. On the axis. So this is because we're presenting this circular coil in two-dimensional. That's why you see that this line is kind of relating there. But actually, when you say that when you have a circular coil, So the physical presentations of what we have drawn there is just like this is your circular coil, and this is the axis passes through the center because it's hollow circular coil. So in the axis, we want to find magnetic flux, let's say here. So remember, because this is the hollow circular coil, there's no any conductor in the middle of the circular coil. We just have conductor on the circumference. My student didn't understand. So let me just define. It's a little bit challenging. I think that let me just demonstrate it by using a rope, because that is all about the conductor. Okay, suppose that this is the circular coil. This is a circular coil, right? And then when you talk about axis of the circular coil, we mean it's an axis. It's not an axis, it's a imaginary line which passes through the center of the circular coil. So what are we finding? We want to find magnetic flux density at this point. So you see that this is the hollow circular coil. So the magnetic flux density at this point, maybe at this point, will be due to the what? Due to the length of the conductor on the circumference, and not at the center. This circular coil is not like this. What I mean is the circular coils that we are drawing is not like this. This is actually because it's two-dimensional planes, but for three-dimensional, this is the circular coil that we are talking to. And that's what I've presented there. So the circular coil, firstly, in first case, we determine the magnetic flux density at the center here. So right now, we determine the magnetic flux density on the axis of the circular coil. Is it interesting? Oh. But for those who want to understand, for those who want just the formula, they don't bother about themselves to understand that what's going on there. So if that the case, it means that now our small segment that we'll be using in our derivation now, we'll take it here and not here. And if you don't understand, today you take here, tomorrow you take here, which is completely wrong. I don't know if Francis, if you are following along. Let me repeat for the benefit of my serious online students. I say that because we present a circular coil, a hollow circular coil in two-dimensional, means in two-dimensional planes. So we take a small segment here and not here. Why? Because here there is no any circular coil. So if you take it from here, you are completely wrong. And you'll be deriving a formula which is not Biot-Sarvat formula. Okay? For those students who would like to understand, that's great information. For those who just want to claim, okay, keep on. But we are here to help you, we are here to transform you, and we are here to change your mindset. So suppose the distance from DL to P is A. Then here we have what? Here we have a line from the center to the circumference of the cycle. And this line is called radius. This line is called radius. So again, let the distance from O to P to be x. Let the distance from O to P, center of the cycle, or the circular coil to the point of P, let it be x. From there, if you're a physicist who love mathematics and you think differently, here also you will see that there is formation of the angle. And this angle, we may call it angle theta. This angle usually used to be formed between a conductor and a line joining a point to the conductor. But for this case, the angle is formed by the axis of the circular coil passing through the center and the line joining the point to the conductor. Okay, physics is simple. Physics is simple. Physics is what? Physics is simple. Very simple. Very simple for you. Okay, so figure 2, very simple. So you study while you relax. Figure 2.2, we say that magnetic flux density, flux density on the axis of circular coil. also this is point Q. Okay, so that's the first step. So let us continue the second step. You have to be careful if you want to understand this derivation. The second step now, we usually recall what? Biot-Sarvat formula for the small segment of the circular coil. I'm still waiting you to stop writing, then I will continue. So recall the general Biot-Sarvat formula. For the small segment, you say that small change in magnetic flux density at the point P, this is equal to the middle free space, times current, times small change in length, times sine of the angle theta, over T, over 4 pi r squared. Okay? 4 pi r squared. Okay. So if this is the equation, we can just call it equation 1. Equation 1. So this equation 1, we have also to do something great before we go to the integration. So we say that this is the general equation. So we call it the general Biot-Sarvat formula. So say the Biot-Sarvat formula for the circular Biot-Sarvat formula for the magnetic flux density on the axis, on the axis of circular coil as shown in figure 2.2 above is given as small change in magnetic flux density is equal to permeability of free space times current times small change in length times sine of angle theta of what? 4 pi. 4 pi what, Johnson? R square. Because you are here, you are not there. That's your formula. It's not our formula. You are still copying. Keep it up. We say the square of the distance is from the point, is between the point and the conductor. This is not a conductor. This is not a conductor here, at the radius. So the actual distance for that case, because this is the general formula, is what? It's A squared. Guys, I tell you, you might think this stuff are very simple because I'm trying my level best to teach them by using a very simple language and have simplified them to the maximum level. But I want to tell you that be careful with this stuff. Be careful with this derivation. Okay. Remember my words. Okay. So it means that with this one, we can call it, this is the second formula, or second equation. Okay, so we go for the third step. The third step, before we apply integrations to both sides, we say that we have to think about what? Tan theta. So to think about tan theta, we say that consider triangle PQO in figure 2.2 above. So if you consider it, okay, so you can consider that triangle. So you have a triangle, a right angle triangle, like this. Here we have 90 degrees, and here we have radius R. This is Q, this is O, this is P, and this is A, and this is X. And here we have an angle theta. An angle theta. Angle theta. Okay, so if that's the case, we have to think here in the general formula we have sine of angle theta. This triangle, rectangle triangle, can help us to know the angle theta in terms of the distance of the side of the right angle triangle. So from this one, so this will be figure 2.3. So from figure 2.3, if you apply rules that we taught you in training, say sine of angle theta is equal to opposite over adjacent, which is R over A. So this will make equation 3. Make equation 3. Then here it is first step. The first step that we have to deal with right now is how can we find A in terms of radius of the circle, in terms of the x. So the first step we say that from Pythagoras theorem, we have it. A square is equal to x square plus r square. That is a square. So we already have a square, we have x square plus r square. So this is equation 4. But what if in some other scenarios, or if you take equation 4 and square it to both sides? So if you square it to both sides, then the square root of a square, it's a, is equal to square root of what? Of x square, r square. So this will form equation 5. Okay? So because we form equation 5, we can go to the fifth step. The fifth step, the relationship between equation 5 and equation 3. What a relationship? We have a is equal to square root of x square plus r square, and then we have r over a. So we can substitute a with this. So we say that substitute equation 5 into equation 3. So to do that, we have sine of angle theta is equal to what? R. What is R? So it is R of what? A, which is square root of what? Of x square plus r square. So this will make your equation 6. Okay? Question. Okay, so you have equation 6. So now we can continue. There's a relationship between equation 2 and equation 6. So what does it make the 6th step? We may substitute equation So we may substitute equation 6 into equation 2. So equation 2 we have what? Small change in magnetic flux density is equal to permeability of the free space times electric current, then small change in length, and then we have 4 pi times A square sine of angle theta, but sine of angle theta is equal to radius of the cycle over square root of x square plus r square. Again, this will make equation what? This will make equation 7. If you examine all of this equation, there's a relationship between equation 6 and equation 4 and equation 7. So if that's the case, we go to the 7th statement. Substitute equation 4 into equation 7. So we have small change magnetic flux density is equal to permeability of free space, current times delta L of what? 4 pi. What is A? A square. So A square, it is x square plus what? R square. Then in the denominator, we have what? Square root of x square plus r square. Then in the numerator here, we have times r. So for this case, we have small change in magnetic flux density is equal to what? Is equal to the permeability of the free space times current times radius divided by 4 pi. Then we have x square plus r square power 1 multiplied by what? X square plus r square power half. Keep copying, keep copying, keep copying, keep copying. And here we have what? Yeah, keep copying. You will tell me the one story of this business one day. So in denominator, we have what? A base of x square plus r square with exponent of 1. We have a base of x square plus r square with a base of a half. Same base at the exponent. So this is equal to permeability of the free space times electric current times radius dr. And here in denominator, we have what? We have 4 pi. Here we have what? X square plus r square power 3 over 2. So we have to still continue with our business. Something still, that is for the small segment. We are still dealing with the small segment. We didn't think about it for the wall or for the entire circular coil. So you have to continue with the business of the derivation. That's why I gave a warning. It's better to listen. So then, small change in magnetic flux density is equal to permeability of free space, then current times radius, then dr, or let's say before dr, here we have what? Over 4 pi, then this is x square plus r square power 3 over 2, or 1.5 in other words. And then, all of this expression we have to deal with it, or we have to multiply with a small change in length of the conductor. So ladies and gentlemen, wonderful students of the Form 6E, this will make equation 8. Make equation 8 and not equation 9. No, this is equation 7. So equation 7. So that will make equation what? 8. So we go to the 8th step. The 8th step is this. Now, integrate to both sides. So integrate from A to B. Okay, it means integrate to both sides of 40 of equation 8. Equation 8. So this is small change in magnetic flux density is equal to permeability of free space. Current terms are what are up, which is radius of the cycle, 4 pi, and then this is what? X square 3.2 dr. So we have to integrate both sides from 0 to magnetic flux density. Then here we have to integrate from 0 to length. From 0 to what? To length. Why should you integrate from 0 to length? This is the arrow. Because we are dealing with a circular coil. So the length of circular coil is that what we call jotting circumference. So for this case, if you integrate from 0 to magnetic flux density, small change in magnetic flux density, all of these physical quantities are constant. You have to take them out of the interval side. Okay? So we have what? Permeability of free space, current times radius over 4 pi. Then you have what? X square plus r square power 3 over 2. Then here we integrate from 0 to r dr. Okay? So in previous derivations of the Biot-Sarvat formula that help us determine magnetic flux density at the center of the circular coil, we taught you how we can integrate this and taught you how we can integrate this one. So simply, we taught you that you have to review, you have to check, to go back of this video and see. So dB, if you integrate dB from 0 to B, this gives us B. And also if you integrate dL from 0 to L, this gives us L. Okay? For that case, on the left-hand side, we have magnetic flux density for the entire circular coil, times current, times resistance, times length, of what? Over 4 pi. Then you have what? X square, r square, power 3 over 2. This will make your equation 9. So we have this equation, but also it told you that the length of the circular coil, which you notate is L, is equal to circumference, which is 2 pi r, or is equal to pi times diameter. So simply we have L is equal to 2 pi r, and this will make 10 equation. So the last step for this journey, which will be the next step, so that now finally there's a substitute equation 10 into equation 9. So magnetic flux density is equal to the unit of free space times current times radius times length, which is 2 pi r, divided by 4 pi. Then we have x squared plus R square over 3 over 2. So we can simplify we can divide by 2 to both numerator and denominator. So magnetic flux density is equal to permeability of free space times electric current. And also you can cancel pi and pi. R times R, it will be R square of what? 4 over 2, which is 2. Then you have what? X square plus R square over 3 over 2. This is the final formula for the single circular coil. This is for single circular coil. Okay? The single circular coil. So, for n turns of circular coil, n turns circular coil. So we say that apply by n right hand side of this formula. So magnetic flux density is equal to it. Is equal to permeability of the free space times current R square. So here we have what? We have twice. Then this is what? X square. This is 3 over 2. So we multiply by number of turns. So this is permeability of free space times electric current, this number of turns, times radius. This is twice x square plus r square power 3 over 2. This is the final formula of Biot-Sarvat of determining the magnetic flux density on the axis of the circular coil. If you have any question about the derivation, don't hesitate to ask me in the comment section. If you have a question about what I've been teaching you, don't hesitate to ask in the comment section of this video. Okay, so if that's the case, then let me give you a question. Example 4. A circular coil of radius 5 centimeter indeed 200 tons. It carries a current of 5 ampere. Find the magnetic flux density. A at the center of a coil, which I told you, so this will be homework 2. B, find magnetic flux density at a point P, which is at distance distance 1 centimeter from the center of the coil, one centimeter from the coil, along from the coil, along the horizontal axis passing through the center. Along there, along the horizontal axis, passing through the center. Passing through the center, Yes, passes through the center. That's the question. When I finish to solve these questions, it will be the end of session 2. You have to join me in the next session, which will be session 3. So let us read the question carefully. A circular coil of radius 5 centimeter and 200 turns and carries a current of 5 ampere. Find the magnetic flux density at the center of the coil. Find the magnetic flux density at the point P, which is at a distance 1 centimeter from the coil along the horizontal axis passing through the center. So Roman A, it's a homework because I told you you have to refer the derivations, and I told you that these are the questions of paper 2. So you have to make sure you write the formula before you use it. You know it. Solution. So solution, say example, this example 4b. So the first step, data given. A circular coil of radius 5 centimeter. Radius R is equal to 5 centimeter. You can change into SI unit for you to be careful. So it's 5 extra negative 2 meter. Then we have what? Number of turns. N is equal to what? Is equal to 200. And carries a current of 5 ampere. Current of 5 watt, 5 ampere. Find the magnetic flux density. This is what is required. Then find the magnetic flux density at the bottom. A point P, which is at distance 1 centimeter from the coil. So 1 centimeter from the coil. So say that distance from P to the coil, which you call R, is equal to 1 centimeter. And this is 1 exponent negative 2 meter. So we go for the second state. Second state, question of paper 2. Derive the Biot-Sarvat formula that determines what magnetic flux density on the axis of circular coil. So I told you I won't waste my time to rewrite it, just refer notes. But for you, you have to practice to derive it once again, several times, until these derivations be in your fingertips. So after derivation, you find the formula of the magnetic flux density is equal to the amount of free space times current times the number of turns times square of the radius of the cycle, then 2x squared plus r square after over 2. So the availability of free space is constant, and you can use the scientific calculator. So one of the constant that you can use in function, you can find in function 991. Just replace constant 33. You get the value. But in most exams, it's given in front of the question paper. Okay. So current will be given 5 ampere, number of turns 200 turns, radius will be given, then what? Then I have what? A. It's 1 cent. But listen, a point P, which is at a distance 1 centimeter from the coil along. So listen, this X means that it's not A, here it is X. Listen, I want to clarify about distance X. Here we have a circular coil, and this is the center. And here we have an axis. And this is the point P. So if you want to deal with a small segment, we take a small segment here. Right? This is the distance between the small segment and the point. But remember that there is no difference between, first of all, remember that X is not a distance from here to here. I made a mistake. X is the distance from P to this point. This is X. No correction. Quickly. I made a mistake. In previous derivation, I told you that X is the distance from P to the center, which is wrong. The distance from this point, so you can call it R. Distance from R to O, this is what you call the radius. The distance from R to P is what you call X. So the distance between R and P, actually, it's a distance between the pointy and the circular coil. Let me demonstrate. Because nowadays we have a digital age students. So don't think much, and then simple stuff. So here is the circular coil. So here is the axis. So the distance from this point P to the circular coil, it's not that hypotenuse of the triangle. It's the distance actually from the center to this point. Because remember that this circular coil is not like this. This is not a distance from here to here. This is the distance from what? From the center to here. So X, according to the question, is what? 1 centimeter. A point P which at a distance 1 centimeter from the coil along what? The horizontal axis passes through the center. Okay? So X is 1 centimeter, which is equal to 1 is for negative 2 meter. For that case now, we go into the third step. So third step, now let us compute the magnetic flux density at P. So we have magnetic flux density is equal to the probability of the free space, which is 4 pi to negative 7 Henry per meter, times current, which is 5, then times what? Number of turns, which is 200, then times what? Radius of the cycle, which is what? 5, so negative 2 square. Then we have here, this is stuff. So you have 2, you have what? X square. What is x square? So x squared is 1 centimeter, so 1 exponent negative 2 square plus r square. What is radius? Radius is 5 exponent 5 exponent negative 2 square. And then all of these expressions will be power 3 over 2. So magnetic flux density is equal to what? So you just have to use a scientific calculator. But remember that if you take this square plus this square, you sum them, then you have to raise power 3 over 2. So you take denominator over numerator. So if you use your scientific calculator, that if you missed one of them, you may order it into also in our online school. Then finally, if you do your computation, you'll find that the magnetic flux density is 1.2 exponent negative, so negative 2 Tesla. So approximately it's 1.2 so negative negative 2 Tesla. Okay. So for that case, we say what? Therefore, magnetic flux density at point P is 1.2 is with negative 2 Tesla. Okay, my dear students, if we have done all of those responsibilities, and you'll do your own responsibilities without ignoring solving the example 2 and also solving the example 4a, and also deriving the questions that we have left, the formula we left in previous example, and derive the formula that we left in this example. All of those work, all of those hard work will actually transform and propagate you into a comfortable zone of enjoying university physics. So I thank God, firstly, who has been with me in preparations of this session. And I would like just again to remind you, for me, I spent several months to master this stuff, to take them from different books, into my mind, or take them from different notes into my mind. And the reasons is the way I have been taught, I was not given detailed explanations, and the derivations actually was too much summarized rather than detailed information about what is this and what is this and what is this. So remember that what I've taught you in session 2 is almost 75% of the mistakes of the mistakes that I did myself during my advanced secondary education studies. I don't want other students also to have the similar challenge that I do, or to find that this stuff are difficult, they cannot be mastered. So, before I end this session again, I would like to invite all the students to visit our Tanzania online advanced bookstore, where you can access the books, the syllabus books, the class notes, and also you may also access, or you may order certificate calculator. You may also order questions and answers books, which you call them reviews. You may also order notes. So these are the sum. This is some of the books that you'll find in our Tanzania online advanced book library or bookstore. So if you do that, how you can place your order, or you can order these books as a student, so you can order these books as the parents that want to buy for the students, and the price is actually affordable, because we're not doing business, we are servicing our students, or we're equipping students in order for them to go far as God will take them. So please send me an SMS or an order SMS. So the telephone number 0759 745331, and then I will make sure that you will receive your fruit. The last announcement, in case you feel from your heart that you want to offer our living God, you are free in Thanksgiving offering. So this program, you're only welcome. This is our our official telephone number to receive the offerings. So you are well invited to join us in doing this great work of the kingdoms of heavens, and in this great work of learning the beauty of advanced physics. And I want to tell you in advance, your free Thanksgiving will be used effectively to pay for the running cost to make more videos. This session 2, once you offer it today, then it will be your seat to facilitate the session 3 to be in air as soon as possible. So that should be a trend. And you should not say that I can't offer because some other people are offering. How sure are you? Okay? So when it comes to the aspects of the offering, really we have to be serious more than what we can do. So this is the end of our session. God bless you, and meet me in the next session, which will be session 3, where I'll teach about magnetic flux density at the point due to the Helmholtz coil. If also we manage to make it, we'll go to the solvent. So until we meet in the next session, this is Olenjolai from beautiful country Tanzania. I love you so much. Join me in the moments of Thanksgiving prayer, and I will leave you that so that you can have a chorus for our national anthem, Mungu ibariki Tanzania. All right? That is what you have to remember as a student. So let us give God thanks and appreciate Him, because He's Almighty God. Our Almighty God, we come before your presence as children. We say thank you for the great thing that you've done to us. Thank you for unveiling the secret of everything. We come before your presence, we surrender all our life. We say thank you for what you've taught your children today. We give you all the praise and glory, because there is no other one other than you. Father, we are here to seek your kingdom and your righteousness, and all things will be given upon us. Father, receive this our daily and night offering, Lord. In the name of Jesus Christ, the Father, we come before your presence, we glorify and we glorify you, our Father, even in this work. Father, I come before your presence, I ask you to distribute these contents, the millions of the students who would like to benefit from this program. Father, I'm praying for all the present and future students who would like to access these contents. Let them be blessed and receive our thrilling thanksgiving. We thank you, our Father, because you heard and answered our prayer. In the name of Jesus Christ, amen. So God bless you and keep you. Don't forget to subscribe into our channel. Don't forget to visit the playlist to see sequential or arrangements of the videos of the particular topic. Don't forget to write comment for me. Just write a comment that, sir, I understood you. That's the comment. Or maybe you can write just a comment that I've listened to you from the beginnings of the session to the end. I didn't understand you at all. So that's a very important comment because it's real assessing me and it's really making me to be actual, to enlarge my tent as well as I can. So may God bless you until we meet in the next session. This is the Olenjolai from Tanzania. See you. Keep enjoying advanced physics.
Ibariki Tanzania, dumisha uhuru na umoja, wake kwa waume na watoto. Mungu ibariki Tanzania.